Hello, my name is Ernesto Alvarez. I'm a student in Universidad Complutense de Madrid, and I want to show you a co-work with Dr. Raúl Belán. This co-work has to be to phylogenetic reconstruction. Let me share my screen. Okay, so the number of the name of this speech is Operations on Nucleotide Sequences to Get Some Parameters of Evolution. This is the phylogenetic reconstruction problem. We have some lineages, some current lineages, for example. We see in figure 1, lineages 1, 2, 3, and 4. And we want to reconstruct a phylogenetic tree. This is a phylogenetic tree. We see in this phylogenetic tree terminal vertices, 1, 2, 3, and 4, that represent current lineages. And we see two internal vertices. They represent ancestral lineages. For example, the internal vertex R represents the ancestral lineage of these 4 lineages, 1, 2, 3, and 4. These rows from different vertex to different vertex represent the evolution direction. Okay, the length of these edges also represent the expected number of substitutions. What is a substitution? Is a change of one nucleotide to another, a mutation. So this is the problem we have to face. I mean, once we have a set of lineages to infer its phylogenetic tree and detail that phylogenetic tree. I mean, to infer about its topology, to decide if it has or not a root and the length edges. In real cases, this, I mean, we could have lineages that are represented by sequences of nucleotides that are not equally length and have gaps. Okay. Okay. There is a main theorem, Hammer conjugation. Hammer conjugation is a matrix equation. It relates to spectral matrices. These spectral matrices are matrix P and matrix Q. Matrix P stores information of the distribution of different substitution patterns on leaves. Matrix Q includes the expected number of substitutions on different edges on a phylogenetic tree. That explains the ancestral relations for these current lineages. Okay, this is the main theorem. So in real cases, it is easier to obtain the matrix P than to obtain the matrix Q, because we have nucleotide sequences for current lineages. This work I want to show you has to do with some procedures that were written to run on system on the computer algebra system Maple that can help to obtain the matrix P. And this matrix P is obviously very important because according to this Hammer conjugation, we could infer the expected number of substitutions on H's for the phylogenetic tree, okay? Table 1 shows 4 lineages with 16 sites. I mean, lineages with 16 nucleotides, okay? Different sites, for example, site 8 is a column of characters, and these 4 characters are placed to these 4 leaves on the phylogenetic tree. But matrix P, that is part of this theorem of Hammer configuration, stores not character patterns, but substitution patterns. So what is a substitution pattern? Okay, let's see this site 8 and consider substitutions from lineage 2 to the rest of lineages to obtain the rest of characters. For example, we need a substitution from T to A, a substitution from T to A, and a substitution from E to T, okay? From T to A, from T to A, and from T to T. These are the different substitutions that we consider throughout this manuscript. Substitutions from A to G and from T to C are transitions. From A to T and from G to C are type 1 transversions. From A to C, from T to G, that are type 2 transversions. This has to do with a model of molecular evolution. It is an assumption that has to be taken into account to implement Hammer configuration. This is matrix P for the for table 2. Table 2 shows different substitution patterns per sites. Okay. For example, at site 8, we saw that we need a substitution from lineage 2 to lineage 1, changing T to A, from lineage 2 to lineage A, changing T to A, and from lineage 2 to lineage 4, showing no change. Okay? So these sequences of 3 integer numbers represent different substitution patterns. Okay? Then what we do is counting how many different substitution patterns are on this alignment, and the corresponding relative frequencies are included into this matrix P according to a particular indexing. And the matrix Q of that theorem, Hammer conjugation, includes information about the expected number of substitutions on different edges for the phylogenetic tree. So in this case, taking lineage 3 as the reference lineage, not the lineage 2 as we considered before for matrix P, we obtain this matrix, okay? In the first column, we have transitions. In the first row, we have type 1 transversions. In the main diagonal, we have type 2 transversions. Table 3 shows an alignment with gaps. Okay. I have included some examples in which I show exactly how I have to include different instructions and different procedures that I program to obtain matrix P. P. See how I included the sequences of table 1. Okay, but there are some procedures that I had to call to work on these sequences of nucleotides. Okay? Procedures are followed by an asterisk. So 1, 2, 3, 4, 5, 6 procedures to compute the spectral sequence spectrum, the matrix P, for these 4 sequences equally length with no gaps. Okay. If we have some gaps, we have to use another set of procedures to fill those gaps. Okay? The criteria I used to fill the gaps is not of biological nature, but of statistical nature. I mean, to reduce the variance, okay? By comparing different character patterns. This was the most difficult part. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different procedures to fill the gaps. Okay, this was the most difficult part. Okay, but it is very necessary to fill the gaps on sequences to compute the Hammer conjugation, because Hammer conjugation assumes no gaps and assumes equally length sequences. Finally, I would like to show a real application. We have 3 different real species of endemic plants in Mexico: Lophiarella microchila, Lophiarella splendida, and Lophiarella flavovirens. These 3 species were given to me by Dr. Ricardo Balán. These are the sequences. They are not equally length and they have gaps. So I had to implement all procedures I showed before. First, to fill the gaps, then to obtain matrix. So this matrix P is very important because in a second work, we could use it to infer the topology of the phylogenetic tree that explains for these 3 species of plants their ancestral relations and the expected number of substitutions from different ancestral lineages to different vertices in that phylogenetic tree. Okay, thank you very much for being in this speech. I hope it is useful for you, and these procedures are available to those researchers that need it. Thank you very much.